Hi everyone, welcome to the second Arduino Acclimate workshop. This one's focused on circuits, so it's going to be really fun. We're focusing on a lot of the hands-on work, so I'm excited. I know I'm going to learn some new things today. If you don't mind, I'd really appreciate if you could scan the barcode right now as a way to log in so we have a track record of who has been making the meetings. It'd be super helpful. So I'll give you a moment to do that.
And as you guys are signing in, we'll take about 3 minutes to complete that sign-in form, and then we'll get started into today's class.
Yep. So thanks to everyone who's filling that out. I'm going to say that I'm going to take another minute and then we're going to get started. Also, if at any point I disappear, my internet's kind of sketchy, so I apologize. I will be back. Okay, let's get the show on the road. So welcome to Arduino Acclimate Circuits. It's the second lesson in the Arduino Acclimate series. We're going to be talking about a lot of the hands-on circuits work. We've got two wonderful people who's going to be teaching us today, and I'm really excited to learn from them. So who are we? What is this entire organization? What is WMC? WMC stands for the Women Machinists Club. We were founded this year by some of the people in this Zoom call who are amazing. Our focus is on getting people of underrepresented genders access to machining, both as a way to build their skills and to build community. It's awesome to be able to just go out and build things, and that's something we want to be able to share with everyone. Our big focus is learning together, and growing outwards together. So that means we're going to be building hands-on skills, we're going to be building our resumes, we're going to be building our networks, and ultimately, we're going out and getting some awesome jobs with some awesome experience. I guarantee you that machining looks so good on your resume when you're applying for engineering jobs, and it's what got me my current internship. So, what can I say? Here is our various forms of social media. So if you want to check us out, we have a website where we are posting lots of different resources. We have a full-on lesson on Onshape, which is 3D modeling. So there's an entire series of lessons on there. We've got information about different types of tools, all of our former meetings you can find there. Also, if you check out our YouTube channel, which is linked from our website, you can watch all of our previous meetings and the information we go over in those. You can also join us on Instagram, LinkedIn, and Slack. We especially encourage the Slack because if you join us on Slack, you'll be able to connect with us and be part of a community where we talk and we share programs and projects and that kind of thing. So hit us up. Feel free to take a photo of this page. I'm going to give you a couple seconds to do so. And also, if you join the LinkedIn, then you will have a connection to all these people later on. So when you are looking for an internship and some of the people have already graduated, you can go, hey, where are you working? Is it a cool place to work? Could I maybe come work at your place? And I guarantee you, the people in this club are really enthusiastic about helping each other. So they will want to say yes. They will want to reach out and help you. Awesome. So Arduino Acclimate. Acclimating is getting used to something new. So what we're doing this year is getting people familiar with Arduinos. The first quarter is focused on the educational aspect, getting everyone familiarized. And then in the spring, we're going to have a big showcase which I'm really excited about. Like I said, we're starting off with Zoom classes on the hardware and software components, building towards the Arduino Acclimate competition in the spring, which is going to be done entirely on Tinkercad, which is a 3D modeling for circuits, specifically Arduino software, that is free and accessible to everyone. This is how we're going to do things in the time of Corona. This is a great opportunity to build out those projects that will get you jobs. You want to have projects on your resume. You want to be able to talk about troubleshooting and challenges and all that jazz. This is a great opportunity. And it's accessible to everyone. So here's where we are in the timeline. We are at the intro to circuits. You can check out all of our previous stuff on the website or on our Instagram or on our YouTube. We are all over the place. And this is the challenge that we've had so far, building a smoke detector. You can find more about this on our Instagram, but right now I'm going to turn this over to Caitlin.
Okay, I'm just going to share my screen here. If everyone can see that. So this is just the intro to circuits and soldering. I'm going to be mostly focused on the circuits part, and then Ruby's going to kind of go over a bit of the soldering for us, as she so kindly has the equipment for that. So this is our table of contents. You can review this later, but basically first half we're doing circuits, and then next we're going to see how to solder those. Okay, so I'm Caitlin. I'm an electrical engineering major. I think I'm like one of the only ones in this club, so that's why I'm doing this. I have cats and I have a recently acquired dog. As you can see, their lovely pictures here. And I have really long hair and it gets windy sometimes. And sometimes it's a mistake to leave that down. And then Ruby, if you want to pop in for your lovely slide.
Hello, my name is Ruby. My middle name is actually Zoom. I got it before the software. Not making any money off of it yet, too bad. Anyways, I'm a third-year mechanical engineering major. I do research with Dr. Robinson, aka the astronaut on campus. If you don't know him, he's an awesome person to get to know. I'd love to help introduce you guys. I am employed by the space government, aka NASA. I did a summer internship that has been extended into a co-op program. And as of now, I will be living in Houston sometime next year for some time that I don't know yet. And also, I love Maker YouTube. Mark Rober, Adam Savage, Snow Geertz, Michael Reeves, the list goes on. I had the great honor of meeting and working with Simone. If you don't know who she is, please find out because she's awesome and I definitely am in love with her. But anyways, I have since started my own weird YouTube channel and I love making things using my mechanical engineering degree and occasionally getting paid for it through my internship. And I'm very happy to be here to talk to you about soldering.
Okay, so first we're going to just do circuitry. There was a little bit of a brush up on this in, I think, one of the previous Arduino talks, but I'm just going to kind of go on real quick. Just the basics. So this is just power, voltage, current, and resistance. They're like the main things that you're going to be working with. So voltage is just the difference in where electrons are. That difference is what makes voltage. If you've got more electrons in one location, that area is more negative. So the area opposite it without the electrons is more positive, higher voltage. Current is when the electrons are moving, they like to balance out. So if they're connected, they try to become evenly distributed. So that's what causes the current, is the movement of electrons. It's a little bit weird, but when current was first a thing, they didn't realize that it was because of the negative electrons moving around. They thought it was because of some positive subatomic particle. So current is in the opposite direction of the way the electrons are moving. So it's a little bit weird, but yeah. So where it's going from positive to negative, that's the way the current flows, and then the electrons are going in the opposite direction. Resistance is just the blocking of the electron movement. So it's just what slows it down, that sort of thing. If you have resistance in current, a lot of the energy can be lost there as heat, which is what can cause, melting or can make a heater, that sort of thing. So that's just the basics of that. Does anyone have any questions on that? Okay.
Question: how many of you have interacted with circuits before? Or learned about voltage, resistance, all that jazz? Can you raise your hand in the participants tab if you've had some familiarity with V equals IR and all that jazz?
Yeah. Okay. If I talk too fast, let me know, because I've done like 4 years of this. It's gotten really deep in there.
Okay, so we've had some people do it, but not everyone.
Mhm.
Welcome
I
everyone.
figured it'd be something like that. So this is the handy GIF Ruby found, or GIF, as the case may be. But this is basically just, it's going from the positive location in the battery to the negative through the resistor, and it's just moving through as it tries to even out the electrons or the potential throughout your circuit. And then that's what creates basically all of the electronics that we see. So one of the really basic equations that we use for everything is V equals IR. So voltage is equal to current times resistance. This is a pretty simple circuit right here. So you've just got a resistor, a battery, and a diode. So if you had, say, a resistance of 10 ohms at this resistor R, what you would be able to do is find the current passing through that resistor. And that would be I equals VR, just like a little algebra swap of the original equation. So it'd be 0.9 amps going through that. And you can use that, like, it gets very complicated very quickly, but that's the baseline of all of the math we do for circuits. Also, voltage is in volts V, resistance is in ohms, which is usually done like an omega if you're going to write it out, the actual symbol, and then current is in amps, which is the A. Something that got brushed up on earlier for one of the previous talks that I heard of is there's 2 different main kinds of ways circuits are often grouped together, and that's the series circuit, which is kind of what we see up here, where everything's in a line along your string loop. And then there's also the parallel circuit, where you've got 2 different components that are connected on either side to the loop. So there's, if you Google it, you'll see a bunch of equations specifically for that setup, and that can help simplify things, but I'm not going to go too deep into the math. You probably won't need it anytime soon. And then the bottom right corner here is just variations of the original V equals IR equation that is very common. So something I wanted to brush up here on is, in this previous slide, this picture doesn't have a ground located, but generally you pick where your ground is. The typical place to put ground is at the negative end, or the not positive side of the battery. So it would be down here. That would be ground, that'd be 0 volts. But the thing is, ground is really relative. It doesn't have to necessarily be the location that is the lowest voltage. It just, you pick ground and everything else is based around it. It's just to give you a reference point for your other voltages at other locations. So you could pick a ground and, oh, my voltage here is negative. Well, that's okay. It's just negative relative to your ground. So as you pick a place and stick with it, you'll be fine. So here, again, the typical place to put it is where ground is 0. So usually that's what you do. But if you're like calculating a circuit that you didn't make, you don't understand exactly how it's working, you could just pick a place and work from there. Oh, and here's a slightly more complicated circuit. So something I wanted to brush up on also besides ground is nodes, which is a place where components are connected. So in this circuit here, each of the nodes is labeled with a little voltage marker. And a node is where 2 or more components connect. So for this circuit, this entire top line here, this is a single node. So it's got a single voltage for that area. But if you have, say, a resistor in between it, there's a new node here. So the voltage is different in these locations. So it's just a good thing to know, okay, this is a node because these are all connected here and there's no components in between. And then that way you know the different places, voltages, potentials will be different throughout your piece. Oh, and then this just has all the currents. I thought it'd be interesting. I don't know. Old lab. Okay, and then one of the last things I want to go over is short circuits, which is generally bad. There are 2 things. There's a short circuit and then there's the exact opposite, the open circuit. Open circuit is like your resistance is infinity. There's no current going through it. It might not even be connected. Nothing's flowing through here. A short circuit is the opposite. It's got ideally zero resistance. Therefore, the potential won't be any different across it. The problem is if you do a short circuit over two locations that you don't want to have the same potential, they'll try to equalize really fast, and that can cause explosions, heat, breaking your circuit, mostly bad stuff. Sometimes it'll just pop. Sometimes everything will go horribly wrong in a fire explosion. Stuff happens. So that's kind of my final warning there. And then I think, okay, that kind of leads into how Arduinos die, which I believe Ruby will pick up, since she's the expert here.
Yes, I have killed a good number of Arduinos in my time. The image attached is one that got turned into the lab key. It was the first Arduino I fried in a public space. I was mortified. Everyone cheered. It got turned into the lab key. Weird experience. But essentially, Arduinos die when you short circuit them, or you apply too much voltage, or you apply voltage in the wrong direction. But one thing that's awesome about Arduinos is that they're really well labeled. So while it is totally possible to kill Arduinos, I think I've actually killed 15 or so. If you pay a little bit more attention, it's avoidable. Catherine. Okay.
Sorry, 15? I hadn't heard the 15 part.
Yes. We do
How many Arduinos have you worked with?
We do lots of
I guess
experiments.
16, but like.
At least she never killed an oscilloscope.
That is true. Don't do that. That's way more expensive. But Arduinos, while they are like more of a microcontroller, thank you, Tara. Arduinos are more of a microcontroller, but just because they look cool and are labeled doesn't mean that voltage and current don't go through them. So you do have to treat them with care so that you don't drop $30 every time you make a mistake, like me. All right.
Should I stop sharing, and do you want to share now and control
Could
it?
you actually flip just a tiny bit and then I can do the video setup on
Yeah,
my
sure.
Awesome. Yeah, so to further that, before we get into the more practical side, because the video I will be showing is an actual circuit that I soldered a little bit earlier today, keep in mind that you're working with current. It can be dangerous. If you put yourself in series in the circuit, you can be in trouble. And if it's too much power, you can actually die. So make sure that you are not working on a circuit when it is live. You should not be holding a wire and holding another wire and then having someone else plug it in. You should have your components on a breadboard or soldered to each other. Seems like common sense, but you'd be really surprised. Be super careful when water is around. Just like toasters don't like bathtubs, Arduinos don't like water. So keep everything dry, be inside or be outside when it's not raining, and make sure you have some sort of ground fault circuit interrupter. I believe, Caitlin, that's that like third prong on an outlet, correct? Yeah.
It's a little more complicated than that. It's something that's usually installed in your bathroom or your kitchen. There'll be like a little button on it you can usually see.
Okay.
They're like $12 on Amazon if they're not already installed in your apartment. Word to the wise, some apartments don't have them installed, and that's a problem because water goes zap. But yeah, $12 on Amazon, definitely worth the investment.
Yeah, a lot of bathrooms will have it just because they do high power stuff and really high humidity. In general, just if you're working with high powered circuits, just be very, very careful.
And even low power circuits, you know, it's not fun. I'm sure my PI hates how many Arduinos I've killed. Like, it's really not fun to have this stuff go badly for your own experimentation, and it's scary sometimes if it goes wrong. So I always recommend erring to the side of caution before beginning so that you keep yourself safe, you keep your project safe, and you can learn in a fun way. That includes wearing pants and insulated shoes. Shirts are like slightly, wear a shirt, please. Definitely definitely wear pants. I don't know if you can see, I am modeling my flame-proof Carhartt coveralls right now. They cover my entire body down to the insulated shoe. And if you don't want to get burnt or electrocuted, it helps to have things that can keep you safe. So if you're going to be doing this stuff a lot, I highly recommend investing in a pair of flame-proof coveralls and some good closed-toed shoes.
I would also just like to emphasize one more time, do not work on the circuit when it's live. That includes if you've got an Arduino plugged into your computer and your computer is plugged into the wall. You'll want to have your computer charged before you start working on the Arduino, or else your computer is working on AC power. And AC power is a lot more willing to zap you than DC power. AC is sine wave, DC is straight line. AC
Yes.
wants to zap you. Don't let it. Unplug your computer.
Yep. And even if it's
Paranoia if they're out to get you.
yeah. And even if it seems tedious, even if you're just moving one wire in Engineering 3, just unplug it. It's a good habit to have. You don't want to get in the habit of moving live wires around.
This is also very much true when you're doing any other kind of machining. I reminded myself of this recently when I was trying to repair our 3D printer and then realized it was still on and was fighting me. Don't be me. Unplug, please.
Should I switch to the next slide?
Yes, please. I think I have pretty brief slideage.
I just have these pictures of
Go for it.
the process. This, I mean, it just kind of diagrammed a prototype. A lot of the pictures that I was showing you are like really abstract versions, but the actual way that you tend to do it, especially in lower level labs, like, I mean, Eng 3, that sort of thing, or any of the electrical engineering classes labs, you'll start with your diagram, and then this is the same piece on a breadboard where you're just plugging everything in. You've got your power, your 2 resistors, your ground, and then this is it on what's called a prototyping board. So these will have copper on the back, but it's more of a, you actually solder it in instead of like a breadboard. So it's like really connected in there as compared to some of the other stuff. So you can see it'll have like actual solders and stuff. Yeah. You've got such a nice one. Mine's like super messed up. Baby's first solder practice.
Ruby works for space government. She gets nice things.
I don't work for the space government. Okay, anyways, that's it. But, you know, there's a little bit of a trick to transferring from diagram to breadboarding, but as long as you pay attention to the way your lines are moving, you should be pretty okay. Tiny fire, make magic wire. That's cute. I like that.
Thank you. All right, welcome to soldering. I am Professor Zoom today. I have no qualifications other than enthusiasm and a few years of experience. All right, so why should you solder? Essentially, if you don't know what soldering is, it's a way to form a more reliable electrical connection between components. If you see the top image on the right, that is what's called a solderless breadboard. Essentially, you poke wires into them. They come with really nice header pins. They make it easy to remove. However, in the bottom photo, which Caitlin and I just touched on, that is a solderable breadboard. And essentially, you can take the circuit on the top and translate it to the breadboard on the bottom. And once you solder it, it is much harder to remove those wires, which is great when you don't want your stuff to fall apart. So once you are done prototyping your circuit, you solder it in order to make your electrical connections more consistent than in a breadboard. And I would like to add that solder has a low tensile strength, meaning it breaks easily. These wires are small. Soldering should not be relied upon to keep your components mechanically together. It should be relied to keep them electrically together, meaning that current and voltage can flow freely. But if you need it to like physically be strong, you're going to play tug of war with your solder components, you need external mechanical reinforcement. And I would love to talk about that after. I didn't include too much on that because I wanted to get to the demo. And the last thing about soldering is it looks pretty cool and sciencey. So with that, let's learn about the equipment we need. Could you please flip the slide? All right, so safety is sexy. No ifs, ands, or buts about it, okay? As you can see, safety glasses. That's the #1 thing for like everything in this club. That should be our club motto is, do you have your safety glasses? Anyways, make sure you have safety glasses, even for soldering. You're gonna be trimming wires, and the last thing you want is a wire to go straight into your eyeball. So that would be bad. Second, if you have longer hair, please tie it up. Soldering is like less rotatey than say a lathe where you could get sucked in, but still you could set your own hair on fire, so it's better to pull it back. And then next, the bare minimum things you need for soldering are a wand, a stand, actual soldering wire, and a fume extractor or fan. Some people think the bottom right is debatable. However, if you're in a closed room with any amount of solder, you could feel some potentially negative side effects. So it is always advisable to solder next to an open window or have a fume extractor. So these are the bare minimum. However, there are some things that make soldering much more accessible, fun, and honestly easier. And I can show those on the next slide. Please. Thank you, Caitlin. All right. So these are some things that are great to have, but again, you don't need them. The very first 2 things I would say, like if you have to choose 2 of these 4 things, I would choose helping hands and wire strippers personally. Helping hands are exactly what they sound like. You can pinch stuff and it holds it for you because soldering is kind of a 2-hand process. And if you're trying to hold your wires and solder at the same time, you can A, burn yourself, B, drop your stuff, or C, a combo of both. And that's very frustrating. So I recommend getting a pair of helping hands. They are roughly $10 to $40, depending on how much money you want to spend. And then next is wire strippers. Unless you are working purely with exposed wire, you are going to need a way to strip the coating off of your wire. And what I mean by coating, if you can see, wire is not like naturally orange. There is no metal that comes out this fluorescent orange in nature, at least not that I have seen yet. Chemies prove me wrong. But what's on the inside of coated wire is an exposed wire. And you get to the exposed wire by stripping off the coating. And that's what you use wire strippers for. And then the other 2 things that are great to have, but you don't need, are tip tin. We can talk about tinning, or you'll actually see it in the next video. And then heat shrink tubing and a heat gun. I can do a demo at the end, but essentially that is a way to protect your wires. Here is heat shrink tubing right here. It kind of like almost feels like a bad hair elastic, or at least these do, like a very flimsy hair elastic. In order to protect your connections, you would move the heat shrink over the wire, solder your wire to another wire, and then slide that heat shrink back over the 2, kind of like one of those finger traps. Use a heat gun, and then it'll shrink down. And now you have no wire exposed, and you're less likely to set things on fire. And it also helps strengthen the connection between the wires to compensate for the low tensile strength. I think that is all of my slides. I might have one more. Yeah, so general prep and body safety, put those glasses on, pull that hair back, grab your materials, turn on your soldering iron. I can't tell you how many times I have been ready to go and I'm like, oh shoot, I have to wait 10 minutes for this thing to heat up. And then while it's heating up, I recommend preparing your wires and components. All right.
Quick question, Ruby.
Yeah.
Can you define what soldering is?
I can define it in the physical sense, but in theory, I'm more of a physical engineer rather than a theory engineer.
Oh, me too.
But essentially, it's when you have 2 wires and solder, you
What is
use
solder?
your soldering. Sorry?
What's solder?
I have an awesome video that I'd love to show to help explain all of this, if that's okay.
That works.
Okay, but like, all right, here's the first way it was explained to me is like teeny tiny welding, which I don't think is the greatest analogy because welding is like definitely for strength, but it's using hot metal to connect things at its basic form.
So you melt metal onto 2 metal pieces in order to create a connection between them.
Mm-hmm. Yep. And it's
Yeah, I think you got that pretty good, Ruby. I mean, it's just connecting 2 pieces of electrically conductive metal with a much softer piece of electrically conductive metal, like gluing something together.
that's a good way of doing it. Yeah.
And when you're soldering, how many wires are you generally soldering together?
I think the best practice, especially when you're new to soldering, is 1 wire to 1 wire or 1 component to 1 component. There are ways that you can solder multiple wires to 1 wire, such as combining them and twisting them. Like if you think about like 2 strands of hair versus like a ponytail, if you twist all of your wires together, and I'll show what I mean by twisting in the video, then you can solder more than 1 wire to another, but you also have to take into consideration the power needs of what you're soldering. Because if you have a bunch of things, but if you connect them all in parallel and then you're short on power, that's not good. So you can solder as many wires together as you want, but it may inhibit the performance of what it is you're trying to make. Yep. All right. Video time, I think. Sure. May I share my screen, please? Oh yeah. 3 basic steps of soldering that you'll see are twisting, tinning, and touching. And it sounds as cool as it is because it's cool. And you'll get to see it shortly. All right. Let's see, we have 1 more question. Between the solder that I choose, okay, that's a good question. There are definitely, are you talking about the actual solder wire itself or the soldering iron? Just to clarify, feel free to unmute yourself and speak too. Yes. So there are different sizes. Like I use pretty thin wire because I typically am working with smaller components, but there's wire with bigger diameters. There's wire composed of different alloys. There is leaded and unleaded solder. I typically work with lead-free, so you're not directly sniffing lead into your brain. But one thing I would recommend is to analyze what you want to build and make sure that the solder you're using is the correct fit for your project, because there's special types of solder that stick better to some metals than other. So I don't have a more specific answer for you, but I hope that was a decent start.
Ruby, do you use flux core solder, or do you apply your own flux? Or
I do not believe that I do flux core. Correct me if I'm wrong.
I mean, the stuff we have at the ESDC has a flux core.
Hey, Caitlin, can you explain what flux is?
Yeah, that'd be great. I don't think so because I don't know what that is personally.
Oh, okay. So some soldering wire will be basically a tube of the solder, which is going to melt. And then inside of the tube is like this weird, gunky, pasty stuff. That is flux. What you can do is you can use the solder wire with a flux core, or you can apply flux yourself, or you can do both. Flux basically just helps stuff the solder stick better. So if you're having trouble getting something to apply, or you want a really good electrical connection that's very clean, you'll apply flux before you start to solder, and then you'll solder on top of that. Or you can use something with a flux core, which I think a lot of typical brands might have a flux core, but I haven't gone shopping.
Yeah, I'm actually looking at mine right now. This is what I use, because it has a flux of 1.8%.
Yeah, so that'll just have a little bit of flux just to help it stick better. So it's not just the solder, there's also a little bit of like, it's basically like oily, gunky stuff. And you can apply it yourself especially if you're working with more delicate parts that need a really good electrical connection, but you don't always need that extra bit either. All right,
Awesome.
go for your video.
Thank you, Caitlin. I learned something. A bad habit of mine is not reading labels. So thank you for telling me that my solder has flux. All right, before I begin, this is cringy and I hope it makes you laugh. I will be pausing it throughout, and also feel free to speak up in the chat if you have questions. Also, there is audio. If you can't hear it, please tell me. All right.
What's up, Women Machinist Club? I'm so excited that you're here today to learn how to solder. My name is Ruby Zoom. I'm a third-year mechanical engineering major at UC Davis, and I like to light tiny fires in order to improve electrical connectivity. So with that, let's embody safety and get started soldering. First things first, safety glasses. If you have long hair, now's the time to pull it back. No hair fires today. All right, now we are ready. Let's go solder. Hello,
very exciting.
We've made it to the soldering station. All right, so today we're going to be soldering a circuit with a power source. I want to solder this circuit in order to ensure the electrical connection is consistent so that our LED always lights up and it doesn't accidentally not light up if we bike with our circuit to Kemper Hall and we get there to show off our final project and oh my gosh, it doesn't work if only I had soldered it. On this table behind me, we have our Weller soldering unit, our soldering wand, sponge for wiping off excess solder. We have our solder wire itself. We have our power source for the circuit today, as well as our other components, a resistor and an LED light, as well as the battery pack. We have our exposed wires that we're going to be soldering to, our wire strippers and trimmers. We have our safety glasses, and with that, let's begin. To begin by turning our soldering iron on. Mine has this awesome control unit where I can set the temperature. I'm currently running at 600 degrees Fahrenheit. Through trial and error, this is the temperature that I like for this specific soldering. We're going to do.
I'd like to pause. Trial and error for what I've been doing with the solder I'm using. There are like specified regimented temperature recommendations that you can totally Google, but I did not and just tweaked it. So 600 degrees Fahrenheit is a bit arbitrary. If it's too hot, that can make it too hard to connect or straight up like melt the thing that you're trying to solder to. And if it's too cold, it will take a long time and the solder will not spread evenly over your joint. It'll be kind of like gloppy, like oatmeal. I don't know. You want it to be more like water instead of like chunky. All right, let's keep going.
Is prepare our components to be soldered to. Apologies if you can't see this. So the first thing we want to do is use our wire strippers in order to strip this wire and expose more of it so we have a larger base to solder to. You can see the wire strippers.
You totally can't see it. There's so many parts of this that are blurry and I apologize. However, I can show you now if you can see me. These are some pretty old wire strippers, but essentially it may be hard to tell. Can you see that those have different size holes in them?
Maybe briefly stop sharing your screen so we can see you.
Yeah, good idea.
I'm spotlighting your video. Can everyone see Ruby now?
I can't see me.
Yeah, she's visible. Especially if you switch to speaker view.
Okay, hold on. Where am I? Hello. Okay. So these are the wire strippers. These are pretty old. They have a spring. They make a nice machiney noise. And as you can see, when we close them, there's different size holes, right? And then back here, don't put your finger in between it, but that is a blade, so you can cut wires. But essentially, when you're working with coated wire, you want to, through trial and error, this is truly trial and error unless you already know your wire's diameter, check through these hole sizes. So if we look back here, can you see how there's space between the strippers and the hole? You don't want that. When you close down softly, you want a firm connection to be made. So we can see here, when I close down, I'm not adding any pressure past closing. The circle is fully closed, right? So if I trim the head off of this wire using the scissors, it's like one of the most satisfying things ever. I hope you all get to experience it one day. We clamp down a bit firmer. This happens quickly. Now you want to add a little bit of pressure so that you'll feel it kind of cutting, like it's now gripping, like I can hold it like this, but I'm not chopping the head off. And then you butt your fingers up to the back of the clippers. So now it's frozen this way too. And then you kind of pull back and push forward. And now the coating is in the wire strippers. And then you can see our exposed copper wire. So I hope that was a better demo than accomplished in the video. And if you go too hard, you can cut the wire off, even in the stripping part. You don't have to be in the cutting part to still cut through the wire. So it takes a little bit of practice. I recommend starting with longer wires. I still use wires that are way too long so that I have extra room to play with. All right, let's go back to the video. Any questions right now?
One point to make with the being able to cut through the wires that I've found is that if you've got multi-threaded wires, so a lot of little bits, it's very easy to cut one or two and have the rest stay together, but you still don't want that to happen. So be careful and check your wires to make sure you haven't like clipped off a couple of the ones on the outside.
Are you speaking in regards to when it's a stranded wire?
Yes, that's the word I meant. Okay. Thank you.
So I'm not going to stop sharing again because it kind of froze the video software and that made me nervous. But if you see, like, you can pull this apart. Do you see how there's two strands now? Can you see that?
A little bit.
Yeah. So think of it like your hair, right? Like if you have hair and it starts like this when you strip it. Oh gosh, I need a haircut. It starts like this. And if you pull it apart, you're basically doing this, right? And you want to keep those the same length because when you're soldering to your connection, if this is your whole wire up here, but you only make that connection with half of that hair, completely leaving out the other half, that connection is not as strong as it could be. So you want to make sure, especially when working with stranded wire, that you twist it before you solder, which I do show a little bit later on in the video.
I think also if you just start with a larger stripping hole and go smaller, just if you're unsure, because I've seen seniors strip away half of the electrical parts of their wire and then try to solder it on, and they're just like,
don't do that. Yeah. if you do strip the actual wire off, that's a-okay. Just like cut off the base and try again. You want to keep all of those strands in there. Yeah. Don't be that senior. Be a cool senior who wears safety glasses and looks cool. All right. It's totally split ends. Yeah. And doing that actually made me realize I haven't had a haircut in over a year, so I totally have split ends. Okay. Any more questions or all right to proceed? I will take that as a sure. All right, here we go.
Different holes corresponding to different numbers for different sized wires. And it's important to use the correct size. You can strip the coating off, but also not cut through the wire. So it's kind of like a Goldilocks situation. It needs to be small enough to strip the coating, but not so small that it cuts through the wire. You clamp down on the wire, just gently, not like you're trying to cut it, and then you pull off And as you can see, you're left with this little piece of coating. I don't know if you can see that. I'm really sorry if this is all blurry. And as a general rule of thumb, I always like to overstrip my wires as opposed to understripping, because you can always trim down the exposed part again. But if you run out of room while you're soldering, it's a little bit harder to strip the wire while you're trying to solder. So next up, we have our resistor. But as you can see, our resistor is pretty long, right? I don't need our resistor this long. So taking the wire strippers we just used to expose the battery pack, we are going to trim down the resistor a little bit, just like that. We have a much shorter and more manageable resistor. Okay, so let's grab our helping hands and we can just squeeze our LED right like that. LED has one leg that is longer than the other, and that indicates that that is the positive side of the LED, or the side that we will be connecting this red wire to. If we flip this around, since LEDs are directional, it won't light up despite our best soldering efforts. So we will be soldering the red wire to the longer leg. Okay, we're gonna take our LED, and this is a little bit of a weird process, but essentially we're gonna separate the prongs and make a cross joint with the two wires. And the reason we make this cross joint, some people call it a twist joint, is to increase the likelihood that our soldering joint is successful. So by twisting the prongs around one another, you are setting yourself up for more successful soldering. All right, so first things first, I know you can't see it, so I'll bring it over here.
One thing I would like to point out, NASA, aka my space government overlord, has standards on how you are supposed to twist components together before soldering. If anyone's interested, it's like really nerdy, but I was so excited to actually get a hold of the document. I can like ask if I can send it to you. So if you're curious, I can teach you how they solder stuff on the ISS. Am I that good at it yet? No, but it's a great document to learn from. And if anyone is like dying to get their hands on it, I will do my best to share it with you all.
We are dying to get our hands on it.
Okay.
Freaking awesome.
All right. I will ask on Monday.
Please share your space overlords. Thank you.
All right. Okay.
Stand. And on this stand, we have a sponge. The sponge is used to wipe off extra solder. And currently the soldering iron is very hot, 600 degrees Fahrenheit to be exact. All right. So now is the time that we get our soldering wand and our soldering wire to take the tip of our solder and melt it on the tip of our wand. This is a process called tinning the tip. Goober of solder is now on the tip of the wand, and we're going to use this.
So I'll pause it because I realized I added the glob kind of out of this screen. If you look at the very, very end of the wand, do you see how like it looks round? Like there's a little round kind of raindrop looking doodad? That wasn't there before. So that is the hot soldering wire that is pulling on the tip of the wand. I have a wand that has a little bit of a chisel, meaning it has kind of a flat edge, which is something I prefer. There's different types of soldering wand tips, but that little circular glob on the very tip is the wire that is now melted and staying hot on the tip of the wand.
To clarify, the wire that has melted, that's the solder, yes?
Yep. Thank you. All right.
This to heat up the joint between the resistor and the LED before we add more solder and complete the joint. We're going to heat the joint up using this tin tip in order to make the flow of the other solder smoother. I'm right-handed, so I hold the wand with my right hand, and then I like to hold to solder kind of like this, like a weird yo-yo with the strand out to the side so that I can feed it with my first 2 fingers into the joint. All right, you'll see it starts to heat up. And then we feed more solder in.
So what's happening here, I realize it's blurry. I seriously apologize for that. My camera is on crack today. I'm realizing watching this footage again. I can grab So this is my unplugged soldering unit, hence the haphazard holding. But what's happening in this picture is we're taking the soldering wand, which I don't know how well you can see. You can kind of see it has a flat tip, right? Like if you're looking, it's flattish. Here, oh, I really don't like stopping share because it really froze the video and I'm afraid about losing the video.
If you set it on speaker view, you should be able to move the amount of the screen that's shared, not you, but all the people watching, so that they can either see a bigger screen or a bigger version of you. I've currently set it so I can see about the same.
Okay.
Somi is asking, just to clarify, the red wire was used to solder? That's an excellent question.
Yes, that is an excellent question. The red wire is what we are connecting using the solder. So they are separate. This is the soldering wire, which is essentially like the fuel that's going to form the joint. And the red wire is actually the physical component that we want to connect. So did that clarify or was that still unclear?
I think
anyone else feel free
I
to
like
step.
to think about solder as glue, or like, you know, a hot glue gun. Let's say you want to connect, for some reason, you want to connect a Sharpie to a compass. You put them up together and then you hot glue them together. And that hot glue is the equivalent of the solder. It's something else that you're adding in to connect things. Solder itself is this kind of shiny silver wire, pretty thick in my experience, that stuff. And it's specifically for connecting things.
Yeah, so this is like a spool or like your hot glue. And then the red wire is getting connected to the LED using this stuff. So yeah, I like the hot glue analogy. Thank you, Catherine. Yes, so I think Caitlin explained tinning the tip well. Ari, did that answer your question all right?
Maybe repeat it one more time just so that the recording can get it as well.
So her question was, why do you have to tin the tip? Which is an awesome question and something I personally thought was a little dumb until I realized none of my soldering was working. And I was like, hello, TA, this is not working. And he was like, oh my gosh, you have to do that. And I was like, I thought it was a suggestion. No. All right. Basically, if you don't tin the tip, you're going to have a hard time like getting the other solder to melt better. Like, I think it actually involves a tiny bit of capillary action, like the sense that it's balling up. And the fact that, oh, Caitlin's giving me thumbs up, that's good. The fact that you like are giving this this very heated ball direct connection to your joint is going to heat up the joint and also set up like a pathway for the rest of the solder, which is coming in on this reel, to spread out. So you think of it like if you have a glass of water, right? And you want to fill it up, but you don't have a sink, you have a huge bucket, and you just pour this huge bucket like over this tiny glass of water. Sure, it's gonna fill up kind of, but if you get a funnel or setting up your tinning of the tip, then when you pour that huge bucket into the funnel, it'll spread nicely in the glass as opposed to like not making a good connection with your glass. Yes? Okay.
Yeah, that's pretty much it. It just likes to stick together like water, so you don't end up with solder just splattering everywhere.
Yeah, or not
rolling into your lap or something.
It loves to go directly onto your thigh if you're sitting down, which is really unpleasant, FYI. Okay. All right. We will keep going.
It will melt along the joint. can let it cool for a second. You can see the fumes coming off. While I don't have a fan, I do have a garage door open, and this wire does not contain harmful materials, so it is okay. Some solder contains lead, which is bad. All right, so that looks good. All right, take over the sponge. We're gonna wipe off the extra solder. Return the wand to the stand so that we don't burn our garage down, and let's take a look at our joint. There is now a firm connection, firm relatively speaking. Before they weren't connected, now they are connected. Solder has a very low tensile strength, so these joints aren't permanent, but more difficult to pull apart. And we have improved the electrical connectivity between these two pieces. All right, so the next step is to take this newly formed connection between our LED and our resistor and connect it to the power supply of our battery pack using the same twisting method. I like twisting it. This is a stranded wire, so it kind of goes everywhere. Think about like your hair in a ponytail. So if you hold the exposed wire and twist it in, see, whee, then you're twisting the stranded wires together, and I find that helps make the connection process easier. All right, so.
I sped this up because twisting is tedious. But essentially we've twisted the two wires again, and we're gonna add solder.
Now we are going to repeat the process of tinning the tip of our soldering iron.
So we're adding that little glob again. So you can see, setting up our tunnel for our water, so to speak. We're heating up the joint.
Our
and
LED,
we add the solder magically fast
resistor,
because I might have accidentally deleted the clip, sorry.
The power side of our battery pack are all connected. You can shake it, you can jump up and down, you can take it to a rave. Step before we can pop our battery in the case and light this up is to solder the ground to the negative side of the resistor.
So now we are soldering the other side. We don't need another resistor. And now that is complete.
It's the moment of truth. We're going to pop open our battery case, take our 9-volt battery. We're going to read the signs to figure out which way the battery goes in, pop it in there. We can return the door of our battery pack. Since we didn't insulate our connections with anything, since they're just exposed, before turning this on, you want to be extra careful that your power and ground are not touching, okay? Because that can cause problems. You don't want to touch wires once they have power source running through them. So
yeah, problems, I undersold that. Problems meaning explosion, short circuit, fire, destruction to your components. Really, really don't touch live wires together. Think of it like, I don't even know, like bad. Just no. Don't cross live wires that don't have insulation. And
don't cross the streams, you know?
Yeah. What we mean by insulation is there is no heat shrink tubing or electrical tape around those components. So if we were to touch metal to metal, there is a chance that the circuit would short itself, and it could kill our LED. It could catch fire if it's enough of a voltage going through it. Yeah, really, really good practice to not touch live wires.
And Ruby, I think it'd be good to mention that the solder you put on the tip isn't the only solder you were using. You also were feeding it in.
Yes, that is a very good point. So the solder you saw on the tip was just the starting point. And then in my left hand, as I was holding the wand with my right hand, my left hand, I was taking my pointer finger and my index finger. And this, some people do it different ways. Some people just start with a really long wire, but I like to start with a little bit of a shorter wire, and you can kind of feed it out with your hand. And as you feed it out. So say this finger is your joint. You're feeding more and more into it, and the wire that is below my finger has melted onto the joint and is forming the connection. So you do have to add more. Yeah.
One thing, I'm just going to jump in for a sec. We are running a little bit over time. So if y'all are free to stay, please do. We're delighted to have you. If you have to head out, totally understand. I'm going to put the link to our Slack channel in the chat. So that way, if you have even more questions, feel free to hit us up there. We would love to talk to you.
Yeah.
Totally.
If you have any questions, you can like DM me too. If you have like a specific question, I don't mind.
That goes for me as well. And just as an FYI, the video has under a minute left, and I won't pause it again if you want to see through the end of the video. Thank you for the heads up, Catherine.
Make sure that they're separate. All right. Before you leave your soldering station, make sure it is turned off. It is unplugged. You can totally set your house on fire, leaving a soldering iron unattended. So before you leave, like you lock your car, right? Make sure you unplug your soldering iron. Right there, okay. So we have our resistor, we have our power source, and let's switch it on.
It's the best feeling right there.
Awesome! Woo! I know Halloween has already passed, but I think this would be a pretty good Rudolph the Red-Nosed Reindeer costume.
Yep, that was the last thing I had to say. I didn't have an outro. I ended it right there. Thank you, past Ruby, for that beautiful ending. Yeah.
Okay, but like how far in the past, Ruby, was this? Let's be honest here.
Roughly 2 hours. Yeah, thank you for watching. Subscribe to my YouTube channel. I'm not joking. I have one. I want to break 300 subscribers. Yeah. If you have any questions, or I can upload this to YouTube if you would like to refer to it. I can totally send out links to soldering videos that have clearer, in focus examples of the solder being fed into the joint, if that's something that interests you.
You should send those to me so I can put them on our website.
Will do. Yes, I am the best YouTuber on the internet, so please subscribe. You can find my.
She builds a void, an infinite void.
Allie has it. I mailed it to Allie on this call if she wants to give a demo. I don't know if she has it up.
Oh,
Nice.
no, I didn't hang it up yet. Do you want me to plug it in?
Yes, please. And yes, you will be able to access the recording of this meeting later.
Yeah, we're going to put it on our YouTube channel, which is linked from our website.
Everyone that's still on here, thank you so much for your time. My apologies for running over time. It's been a joy, and I hope you have learned something.
Yep. Any last minute questions?
Oh, sorry, didn't mean to interrupt, but I also want to say thank you to Kathy, Caitlin, and Ruby for setting this all up and all the work that's been put in for these PowerPoints, emphasis on safety, and then also the video content. Again, would love to emphasize that Arduino Acclimate is a program that gives an opportunity to all students interested in learning physical computing through Arduinos, circuitry like today, and then for our next class, we'll be going over programming. So how to use Arduinos and how to program with them. And then after this class, I highly recommend you to fill out our feedback form to let us know how we can continue to improve these classes. And from our first class, we received feedback that you guys would love to see more hands-on in addition to the PowerPoint presentation. So hence today, and really kudos to Kathy, Ruby, and Caitlin for setting that up. Also, if we can probably go back to Ruby and Caitlin's contact information so that you guys can jot that down in case you guys have any questions. Feel free to reach out. And as Kathy said earlier, that WNC Women Machinists Club has such a nurturing community that we always want to help each other. And we hope that our members will embody our club's culture and be an example for new members who are coming in and for other clubs on campus as well. So I will be sending out an email to those who have attended today as you have signed in using that initial sign in Google form. I'll be sending out a follow-up email for the feedback form, and I highly encourage you guys to fill that out. Yeah, if you are Ruby and Caitlin, you can put down your contact information down in the chat, which you did already. Ooh, okay. And then, yeah, we'll see you guys. I'll see you all at the next class, which is happening, I think, in 2 weeks.
Yeah, and for anyone who's interested, my latest like soldering past a single LED has been this thing that Allison has in her screen. It is an infinity mirror that
I can plug it in while you talk about it, but I forgot the order that I'm supposed to plug it in, and I don't want to break it.
Okay.
It's such a mood.
Plug in the Arduino first, and then the circular cable at the bottom. That one goes second.
This one goes second.
Yep.
There's
so
an
the white
order
box
to it?
first.
The white box goes first, yeah.
Okay.
Caitlin, there's only paranoid.
I'm so scared I'm gonna break it.
I mean,
Okay.
you know, worst case, you make an explosion in a fire.
There it is. Can we like spotlight Allie's video?
Infinite void, baby. Check that out.
Could you show the back too, or like
Side view so they can see how deep it actually goes.
yeah?
Yeah. You want
So,
to
like,
see
can
the
you show the-
back?
So it's
This is
actually
the cool part.
yeah. So honestly, this was a little NASA would be sad, I think. Let's put it that way. But because that is not like a custom PCB board, that's just a soldered board with some transistors. And then I drilled wooden blocks so that the board would not be directly resting on the mirror. And then the electrical tape serves no purpose other than cable management. Everything you see there is hardwired and insulated.
Cable management is important. I have to go, but I'll see you guys later.
Thank you, everyone.
Thank you, everyone.